All right. So I sent that email out yesterday due to several reasons. Before, and it still says this in the outline, the lecture was required. You had to do it whether you like to or not. Even though, like with the assignments, you could effectively choose not to do the assignments. I don't care. It affects your grade accordingly. That's what I'm doing with the lecture now. You don't have to do it. If you can choose not to do the lecture. You won't get those points, to be clear, but you could just choose not to. It's not required anymore. Okay? So if you haven't replied to that email, reply to that email. Even if you already picked a topic, I am operating under the assumption, unless you already replied to the email again, I'm operating under the assumption that you're not doing it. So if you want to still do your topic, email me. If you don't want to do your topic, email me too. It just makes things easier for me in bookkeeping and understanding. Once I have that, and I have a sense of who's doing what, and I did see your email, yeah, I'll let you know. I didn't even realize, I actually had 3 people that wanted to do artificial life. I didn't even realize I had 2, so anyways.
I just kind of looked on the website. Anything that I saw that was like taken, I just said I can't do that.
Well, the problem is I was really slow at updating it. I was really fast at updating it, and then things happened, and then I became very slow at updating it, and that created issues. What was I saying? Yeah, once I have a sense of who's doing it, and then I'm going to go through and I'm going to send a similar email about the project to get everyone to reply to that email for the project, because otherwise I can't keep track of anything. The project is still required, but I want to get a sense of who's doing the presentation, and then I can work backwards and figure out when everything's going to have to get scheduled. Because until I know how many and what, I can't schedule anything. And to the people who replied, I don't think any of them are here right now. Several to the email, I said, just confirm if you want to do it or not. The number of replies I got that were like, maybe. And I was like, no. What's up?
I responded to it.
You did, awesome, good stuff, good stuff. But some people, yeah, they replied with maybe. I'm like, no. The whole point is scheduling this. I need to know. Anyways, any last questions? All right. So, actually, I should open up PyCharm, because we're going to be doing some DEAP today. You don't have to use PyCharm if you don't like PyCharm, but I have PyCharm. Let me, no, stop it. Well, once, no, come on, recent projects. There we go. If you have, if you set up the courses stuff, like if you pulled from the GitHub and you ran this setup for the course, you already have DEAP. If you install DEAP another way, that's entirely fine. GP, no. How do I want to do this? Do I not have any, You know what, maybe I won't even bother going along with you. Here's what we're going to do. Okay, DEAP. All right, DEAP. Due to the complexity of implementing a genetic programming system, which, by the way, I want to be clear. I think at this stage, there should not be an issue. If I made an assignment that said, go implement a genetic programming system, I'd expect you'd be able to do it, but I'm not going to make you do that. I'm going to say, because that's not, to me, that's not the point. The point is more using these tools and understanding the results and working with them and, analyzing stuff. So due to the complexity, like very few people go and implement their own genetic programming system from scratch. Instead, they use an existing system, and we're going to use DEAP. And you should have already had that already set up and ready to go on your computer. So remember, we're doing symbolic regression. Usually, we're going to get our data in tabular form. That's a fancy way of saying it looks like this. Okay? Rows and columns. Columns are the variables. Rows are observations of that variable. So in this example, we're going to have arg3. That's going to be what we're fitting to. So we want to find some function of x1 and x2 that gives us y. All right? If that's unclear, you're thinking too hard. I want to find some function f, that's going to be the y, of x1, x2. Okay, that's what I want. This is going to be, effectively, this will be y hat. Okay? That's what I want. Now, what is this function going to look like? Is it going to be something like x1 plus x2 divided by 2? Maybe. I don't know. But that's like what I'm looking for. That's what symbolic regression is going to be looking to do. So the above data is provided in a CSV file. For this example, yeah, okay. The data is formatted such that the last column is always the dependent variable. The last column is always going to be what I'm fitting to. I know it's kind of backwards, but the last column is always going to be like the left-hand side. All right? The data generated, this data was generated by some unknown phenomenon. Okay? It was generated by me, but some magical phenomenon that we want to model. We want to find something that effectively describes the relationship between x1 and x2 and y. And we get y hat. Remember, there's a difference between y and y hat. Y is going to be the true thing, and y hat is going to be the prediction of that thing. You'll notice from this data, there's a lot of floating point number crap going on in there. Yeah, it's because I added random noise too, because nothing's never that pretty. So, you know, it's always going to be a close approximation. So here's some code I have in some, if I were to go, I think, please tell me I didn't close this. Source. GP, symbolic regression. Yeah, if we go down here, this code that you're looking at here is that code there. It's literally taken from that. When I generate the website, it goes and it steals the code from there. So here I am loading up the data. I used a bunch of Pythonic code here, whatever I'm saying, okay, OS path join the relative resource. This is some constant data file. They are defined up here. This is where I have it saved. This is the name of the data file. I load it up. If you're like, what the hell's going on? You don't have to do it this way. This is just the way I did it. I thought it was easy. This is just some list comprehension for x in the data file. Split x on the comma because x is going to be a row in that data file, like one whole line. We split it on commas, and then we map the float. We're going to convert everything to float in that, and then we're going to map it to, we're going to then turn it into a list. Yeah? Okay. But you'll notice and you're like, wait, why is it a list? There's an outside list. Well, yeah, we're going to have a list of lists. The outside list is all of the rows. The inside list is going to be all of the columns for each row. All right? Then what do? Well, I say the independent variable is everything up to but excluding the last column. And the dependent variable is just the last column for all observations in the data. Okay? So effectively, what I have now is, do I show what I have? Yes. So this is effectively what I have. I will have independent variables, 3.168 blah, 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 3.3 blah, 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 and then the corresponding dependent variable is negative 5.755. If I go up here, that's like literally that. Okay? Yeah? Happy? The next row would be negative 3.5 whatever, 1.3 whatever, and then negative 2 point whatever. See? So that's what it is. Okay? Cool. We can think of it. And in fact, this is often how we think about this in the regression world. You've got a matrix called X that's going to be like negative 3.168 3.63 plus 1. Oh, I'm off by 1. Whatever. Ignore the floating. Ignore that for now. Negative 5.75. Oh, wait. No, that's not a comma. And this is y. Okay, so x is this matrix of all of the independent variables in the rows, all observations of those things. And then y is a vector that corresponds like row to row. Cool? Cool. All right, evaluation. Oh, I was thinking about, remember last time or 2 times ago we were talking about mean squared error? You can think of it like this. When you have like a mean absolute error, every improvement follows a gradient that looks like this. It's this nice linear improvement. So when I mean gradient, I mean like I'm standing here and it's a minimization problem. And I were to say like, okay, well I want to take a step towards the right direction. Which step should I take to maximize my most? Well, I want to go that way, right? Because it slopes towards that. When you do something like mean squared error, of course I don't have an eraser, we effectively slope the gradient. We slope the slope a lot more. I mean, hell, it's squared, so it's going to go like this. So if I have a couple of people, no, that's a bad example, because they're around the same. If I have to tell one of these 2 people, this is not a perfect analogy, but I'm sure it kind of can make it make sense. Because of how it's sloped, if I take one step in like 1 unit that way, or the same unit like that way, really I should draw it like that, like I will get a much bigger improvement where it's like a higher slope, and it's a higher slope the further away I get from the correct, like the minimal answer. So when you square it, it means like the slopes get even steeper, meaning like I'm really inclined, like every step I make here is worth a lot more than a step I would make here. Yeah?
Is there a reason to not square and do like a higher exponential?
You totally could. I just think that square does the trick. And you'd have to use, I mean, yeah, it would have to be even. I'm sure you could, but I don't know why people don't use a higher one. I assume it's like, it's good enough, but that's a good question. I don't really know why. Anyways, mean squared error. And if you're scared by math, this is just like, okay, mean squared error. Why? Well, it's the sum of all the differences between, okay, I have a function that predicts y hat. I get y hat back, okay? And I have the real observation. So let's say I have a function. My symbolic regression generated a function, and it gave me back the number -6. Well, -6 is my y hat. That's my prediction. And what y really was -5.75. So I calculate the difference, I square it, and I add all those up, and then when I'm done, I divide it by n because it's the average. It's the mean squared error. Cool? If that's spooking you, once again, you're thinking too hard. You're thinking way too hard. I remember the moment in my undergrad. I mean, it was early in undergrad, but still, there was a moment where I realized, like, wait a minute. That math syntax, that's just an algorithm. Like, that just means, like, loop over everything and add it up and divide. Like, it dawned on me that mathematical syntax actually was, like, equivalent to, like, the algorithms I was writing. And I was like, oh, my God, it's the same shit. They warned me about this. So, yeah, that happens a lot. Because they're just operators, right? They're just operators. And it's funny, because you can actually build basic arithmetic up from counting. You start with the premise that I can count. So what is addition? Well, addition is count how many times, right? So if I say 5 plus 5, we'll start at 5 and then add 1 5 times. Okay? And then what's multiplication? Well, that means like add 5 times. And then what's exponential? Well, that means 5 times 5 times. And so on and so on. And of course, there are inverse operators, minus and whatnot. But with just counting, you could build all these operators, which are actually just like looping over counting. And then like nested loops, and it's crazy. Anyways. All right, yeah, mean squared error is perfect. Any metric could be used, but mean squared error is very popular. One of the reasons it's used is because it punishes bigger errors more. If the difference between the observed and estimated value is 1, the squared error is 1. If the difference is 2, the error is 4. If it's 3, it's 9. In other words, it's much worse to be very wrong than it is to be a little wrong. So it would encourage the algorithm to improve on the bigger errors more. That's what we want. So how do we calculate it? That's just that, okay? I use some fancy Python stuff here, mean squared error, but running error squared sum for xs and y in zip of those two things, calculate y hat. That's the compiled individual. What's the compiled individual? That is basically genetic programming generated a tree. That is the individual. But we can't, it's just a tree. We can't calculate anything on the tree. We can't use that tree as a function. So we have this magic process to compile the tree into something that can be run as a function. What that is, we'll see in a moment, but compiled individual is effectively, that is the individual. And it takes the argument. Has anyone ever seen this syntax before? Not quite. You're thinking more like C++. What that means here in Python, has anyone else seen that syntax in Python? It's pretty cool. Do you know what it is? Effectively, yes. So what it is, XS is a list. This is a list of length n. And this is a function that takes n arguments. It requires n arguments. But if I just give it XS, I gave it one argument. I mean, it's one list that's filled with everything. This just basically means like unpack it. So you take the n, the list of length n, take each of the n things out and just kind of like put them there as if they're all the arguments to that function. It's a handy way of, it's just handy syntax. That's all it is. If you don't like the syntax, you can forget it. Running error squared sum. You take the difference, you square it, and then when you're done, you just divide it by the length of the dependent variable. Yeah?
Is that syntax the same as doing like for I in XS run compiled individual? Like, is that running it on each individual instance?
This, no. So XS will be one row, and Y will be, XS would be like this. But this would actually, as far as Python's concerned, this would be a list. Right? So we have one row, and the star XS means, okay, take these out, and just they are the arguments to that function. Is that your question?
No.
Oh.
What goes into y hat? Like,
What goes into y hat? The result. So I have some, remember, y is what it really is. Y hat is, I don't know, let's say the function my genetic programming system came up with was x1 plus x2 divided by 2. I don't know. So someone plug in, so what's negative 3, 3, so that's going to be like, you add those two, the 0.5, let's call it 0.5-ish. Divided by 2, that equals 0.25. So my y hat is 0.25, is what I predict it is. But what it really was negative 5.75. Not very good, but based on what this was. So this would be an individual from the population, an individual chromosome that's been compiled. And again, compiled is just a fancy way of saying there was some process that DEAP has built into it to take a tree structure and turn it into a function that can actually be run. That's the compiled individual. Yeah?
how do you know compiled individuals can have enough, like, what's the parameters for it?
Arguments?
Yeah.
Because if it didn't, I implemented something wrong. because I implemented it in a way where the compiled individual, the genetic, okay, maybe it'll become clear as we carry on. Long story short, when I generate these trees, each tree knows this is the set of arguments or parameters you'll have. You might not use them all, but each function in the population, each tree, can take, in this example, we'll always have an x1 and an x2. It'll always have two arguments, always. The tree might be something as stupid as return 4. So the answer is always 4. It takes an x, it took these two values, but it didn't do anything with them, and it just returned 4. So each individual chromosome will take the two inputs. And why the two inputs? Because it was designed that, well, I knew there's two independent variables. Independent variables is that there's two columns here, okay? I knew that. So when I told the GP system, now make trees with how many arguments should each one have? 1, 2. Why? Well, because that's how many it would need. I want functions that are built to work on these two arguments. It'll probably get clearer as I carry on and you kind of see how all the pieces fit together. Other questions, though, about the mean squared error here? Language. So with symbolic regression, genetic programming will search space of mathematical expressions. This includes both operators and operands. The language is the set of operators and operands that the GP system can use in the search. The trouble is, it's not always clear which operators and operands should be included. You might say, well, just throw a bunch of, look, make the language as big as possible, right? What operators, we're doing symbolic regression, so what could we include? Plus, minus, divide, multiplication, exponent. We could do logs. We could do logarithms. We could do e and ln, like the natural. We could do sine. We could do trig functions. We could do all those things. And we could add more and more operators and operands to our search space. But we're making our search space bigger. Look, it's already an infinite size search space, but we know that, some infinities are more crappy than others. So, do I really have a reason to believe that there'd be trig functions in this? Maybe. I don't really know, actually. But if I don't need them, I should definitely not include them. I want to exclude them to reduce the search space. So you're always playing that game. You never really know. And I'm not going to tell you on your assignment. All right. So fortunately with symbolic regression, there are some, with symbolic regression, yeah, those are your typical ones, right? You're going to want your arithmetic operators. By the way, you can define your own functions. There's nothing saying, if for some reason you're I have a feeling I'm modeling some natural phenomenon where I really have a feeling it's going to be some function, but within that function, not only do I expect there to be additions and divides, I really expect there to be an x squared plus 7. So I can add that to my language where you have an x squared plus 7 operator where it just automatically does that for you to you speed up the search space. But again, you got to be careful with biasing your search. So with symbolic regression, it is easier than your general purpose genetic programming because usually you stick with your arithmetic operator, maybe some trig, I don't know. But there is a problem with divide. Yeah?
If you're doing something like the x squared plus 7, is that a function that's usually more complex or less complex?
In the end?
Instead of x squared plus 7, would it be a more complex function?
It could be whatever the hell you want it to be. So there's no, x squared plus 7 I pulled out of my ass.
Yeah.
You can make it more complex, you can make it less complex.
But due to the simplicity of it, I don't know, if somebody was going to hard code having one of those instances there, would they opt to do something more complex because the algorithm is probably going to find that on its own?
I'm not sure I understand your question. Remember, the goal of using symbolic regression is, on the assignments, we're playing a game. But in reality, it's, I got a problem, and I want to solve it. So I'm not going to make my problem more difficult. I already have my problem. My problem's like fixed, and I want to solve it. And I want to do everything I can. I want to squeeze every ounce of potential goodness out of my GP system. And if for whatever reason, I think x squared plus 7 is very important, I could add it to my language. And then imagine the final result is x squared plus 7 divided by 2. If x squared plus 7, like think about what that would mean in terms of your tree. If I didn't have x squared plus 7 divided, like x squared plus 7 in there, my tree would have to look like this. That's what the tree would have to look like, right? Yeah, whatever. You get the sense it's kind of big. But if I did say, well, no, x squared plus 7, I really think that's important. There. Like suddenly it's so much easier. But I bias my search because maybe x squared plus 7 is bullshit. Yeah.
Is it there as a...
It is, yep. Yep. So like you'll see how like these things are defined. But basically I write a list of functions for Python. You know what? You'll see very clearly when I show you protected divide right here. We have a problem with division. I can't just throw division. Now look, I'm dealing with floating point numbers. This isn't going to be an issue. It is hilariously unlikely that the following is going to be an issue. But I might be dealing with integers, and if I'm dealing with integers, this sure as shit going to be an issue. Protected divide. Who can tell me the problem with having divide? I could do something like this. I got a problem. The GP system will try to divide by 0. And then what do? How do you deal with that? Ugh. I mean, you can have it try to, like, do you want to, like, what do you do? Well, here's what you commonly do. Return infinity. There. It returns infinity. If the divisor is 0, return infinity. Some people, actually, I'm going to come back later. Why infinity? Well, it's a way to basically say, look, if the divisor isn't 0, you just do the division. Here's the function. Okay. One sec. If the divisor is not 0, you're good to go. Right? You just do the division. If it so happens to be 0, return infinity, right? Because we could always say, well, was it really 0? Maybe it was just really close to 0, and anything divided by something really close to 0 is going to be like near infinity. Besides, we obviously don't want something in here that's going to return. We don't want anything in here that is divide by 0. That's obviously not going to be useful in the final function. So this would make any mean squared error absolute nonsense. And it would give this function a really bad fitness if we're minimizing mean squared error. So this individual where it's trying to divide by 0, we kind of want to die off. So that's what we would do. By the way, I lied. This is not what you commonly see. You commonly see something entirely different, which I think is catastrophically and categorically terrible. What you commonly see, and I don't know why, and these people should be punished. They need to get sent to their room or something, because what you commonly see people do is if you ever try to divide by 0, they return 1. Yeah, what the hell? What? That doesn't make sense for several reasons. Or maybe they'll return 0. Either way, it doesn't make any sense. There's no reason to do that. It's wrong, like mathematically, intuitively, it makes no sense. And also, in terms of like, oh, suddenly like 0, okay, 0. I mean, that might be giving you good mean squared errors in the end, when you've got a function containing bullshit. Like, what's going on? So yeah, don't do that. You go through the text for this class, they even say, yeah, do that. No, do not. I think the documentation for DEAP may even say do that. Don't do that. It's terrible. I don't know. I'm willing to bet you ask most people, why do you make it 1? They'll be like, I don't know, it's because of what I was told to do. And whoever came, and you probably follow that line all the way back to some asshole that was just like, I don't know, I typed it once. Terrible idea. It makes no sense. So don't do that. Do this. You could do something like, if you don't like infinity, because infinity can maybe cause issues in the calculations later, you could just make it some arbitrarily large number like 99999, like whatever. You could do something like that. Yeah. Anyways. Well, you had a question or something, comment?
No, I was guessing what you said.
Yeah, perfect, cool. All right. So how do we set up the GP language? Well, this kind of goes to your first question. So we create something called, this is genetic programming, we create something called like a GP.primitive set. GP is imported. We create a primitive set, and the top one we call main because that's like the function. Okay, not main like it's the main function of a whole, I mean it kind of is, but it's main. That's like the top of f of x. Okay, we're there. And then the second argument there is how many independent variables are there? Well, I just, based on the data, it's the length of I picked the first row because they're all the same length, it doesn't matter. The length of the independent variables, meaning if this was 2, that's 2. If we had 47, it would be 47. Each function would expect to get 47 arguments then. Then we go and we add primitive operators. Now, you might be saying operator.add. This is just Python-y stuff. There is a library in Python called operators. And operators.add is literally the function B. That's it. It's just a quick and easy. I didn't need to write each of these functions as actual functions. But Python, like GP or DEAP, needs these things to come in as functions. So within the math library, or the operators library, I just wrote them in there. Because remember, this is Python, where you can pass functions as arguments to functions, which is pretty neat. So I do add. How many arguments does add take? 2. Subtract. 2. Multiplication. 2. Protected divide. This one didn't come from the operator library. That's the one I wrote here. I wrote that. And if we go here, let's go look. Do I have it up here? So protected divide I wrote right here. Okay? If I scroll down, and then I included it right there. It's just the name of the function. So the function, protected divide, it takes 2 operators. I have another operator, the negation, right? Just if it's negate it, whatever. Multiply it by -1, I guess. And with something like that, how many arguments does that function have? 1. It only needs, it's a unary operator. And then finally, we add our constants. This, I'm calling it randint. I just need to give it a string that's a name. I can call it whatever I want. And then you see this like partial. This creates a partial function. For those of you that remember something like this from like math, this is just the fancy code that makes it work. You create a partial function that's going to be the randint from -1, just whatever. That's how it works. That's the magic code to make it work. The first line creates the primitive set object. This is where the language operators and operators will be added. It also specifies the number of independent variables that each function will have. And as discussed, the independent variables were stored in some list somewhere. Each operator is added to the primitive set along with the number of operands each operator requires. The operator is the first argument, and it's passed as a function. The function, not a function call, but as the function itself. How do you know it's a function and not a function call? Well, in Python, that's easy. There was no parentheses, right? That would be a function call if there was parentheses. I mean, this would be incorrect because add needs 2 operators. But let me scroll up. That's how you know, like, that's the function call. This is just the function. If you don't believe me, let me go to Colab real quick. And for those of you that don't know, this might be really weird to you, but I'm going to show you right now anyways. And this is a cause of a lot of confusion among early programmers because they make the following mistake frequently, and it's always a nightmare to figure out and kind of amusing. Okay, so I wrote a function, it just returns the sum of the two arguments, right? So print, if I do this, obviously, I didn't call the function. I never called it. That's just the name of a function. I never called it. And Python will be like, well, that's just a function, and it's stored at this memory address. Well, really, it's actually more of the hash, but it's the same thing. That's where it is. If you want to call the function, well, that's easy. You do like 5 and 4. And now we get back 9. We called the function. Now, because of this, you can pass functions So if I go back to ASD, I mean, this is kind of neat. Thank you. So now here, I can pass this function, and let me do this. There. Now you can see a little better, right? I can pass the function add as an argument. So it's a parameter now inside of this, and then when we do op, well, what's op? Well, it was add. I can go and I can change this out to sub, which is kind of neat, right? You might say, well, what's the whole, why? There's a lot of neat reasons why this is cool. But also because of it, you'll notice that op is a parameter that effectively became the function, whatever was passed here. This works like any other variable. Or let's say add, and now I can say, so look, first if I were to do add, like that, obviously that gives me back 9. But I've also effectively given add an alias, QWERTY. And now QWERTY is the same thing, which is weird, but we can do that. Yeah? Can I modify it? So I can modify what it references, but I can't go in and modify the function. So I could be like, well, now equals 8. And well, now this won't work because it's 8. So I can modify. Remember, QWERTY isn't the function. It's a reference to that function. Everything's a reference. Even the things that are primitive types in Python are actually all objects, by the way. They just pretend to not be. It's weird. But for good reason. This, though, causes a lot of issues because the number of new programming students that accidentally do something like this and then later try to say, oops. This type of stuff creates such a headache for new programmers because they accidentally did something like this. And then because it's Colab, that line of code was still run. It still remembers that fact even though they deleted it. So they're like, what the hell? What are you talking about? Print, what, add, argue, what? Yeah, so just, if you're not used to Python, beware. A lot of new programmers and experienced programmers think Python's great. It's so flexible. It's nice. Why don't we use it? Everyone should be learning through Python. I think if I were to teach 162 in Python, that would be a giant nightmare. That would cause so many issues because Python lets you do crap like this, where Java was like, stop it. Don't do that. Java's got the authority that's protecting you from yourself. Python's like, yeah, cool. Do what you want. You totally meant to do that, right? Yeah, no. Anyways. Finally, we added the constant. There's no guarantee of the suggestion that this is a good language. What I showed you here, this is by no means a good language. It's fine. There's nothing wrong with it, but I'm not saying that this is oh, this is what you want to use for symbolic regression. No, that's not the case at all. Yeah. And then setting up. Well, I have this creator object. By the way, with this, you go and review this that I give you, right? This is a good point of reference for your assignment and everything. But we go and we have this creator thing, and we define the fitness, right? We have to specify the weights. -1 because, well, first of all, this always needs to be a tuple. Okay? Now, for those of you that did what you were supposed to beforehand, which is read through the documentation of DEAP, this makes perfect sense. For those of you that didn't, go read it. And the weight is -1 because it's a minimization problem. If we wanted to maximize, we would just make it 1, +1. We create a toolbox. We register this tree generation strategy. This is just the magic code to generate trees. You can go, if you read through the documentation, you can try different strategies. That's entirely fine. You define what an individual is and how you generate it. You define what a population is. You define how to compile the population. How do you convert the trees into something that can run? This is already, this already exists. This was given to you by DEAP. This is the magic code. We register evaluate with the mean squared error fitness. This is just, again, a lot of magic code here. We register how we're going to select, how we're going to do crossover, how we're going to do mutation, and how we're going to do, mutation and how we're going to generate the mutation subtrees. Right? If I, basically, based on the mutation I selected, I selected a node, and I want to replace it with a new subtree. Well, how do I generate that subtree? That's what this is all defining. If you look through the documentation, you will find a lot of different examples on how to do this. You are very much encouraged to do so. Any questions before we stop for today? Yeah?
It's more about symbolic regression itself.
Sorry, say that again?
Can you use calculus as an operator? Like, do you ever make software in calculus?
So what do you mean? Do you mean
Like, for one of the operations, can I have in the same way that
get the derivative?
yeah.
I don't see why not. But that's more algorithmic. I mean, I don't see why not. Yeah, you could totally, look, you could do whatever the hell you want. All that matters is that it's an operator that takes some input and produces some numerical output. Now, that's going to get tricky because if you're getting the derivative, you're returning a whole function. So, but at the end of the day, that whole function would have had to have been evaluated to a value. Because if I have a tree, and this is do the derivative, dir, and I've got some subtree, and it effectively means the derivative of that subtree, or actually it would probably be a single, but that would need to get evaluated to, that would be tricky. By all means, have at it. For this assignment on the sample data I give you, you ain't going to need it. I know, big hint for today. You ain't going to need that. Usually, though, we like what we call closed form solutions, which is a fancy way to say we don't want any of that shit. We want a nice, clean function. We like those things. Recursive functions, can you do it? Yeah. Do we want that in real life? No. We really don't want that to be happening. Anyways, we got to wrap up. So I'll see y'all later. I moved the due date back another week, right? Yeah, okay. There's something about you guys this year. I'm going so slow. I like it. I think it's better. I think we get a chance to talk about these things, a little bit of a discussion, which is a good thing. But in general, man, we're moving slow.